Good morning, good afternoon, good evening, ladies and gentlemen. Once again, you are welcome to attend this class on renewable energy technologies. I'll be speaking about solar cooling as our chapter 4. And once again, my name is Emmanuel Ramdi, and working with Dr. Yao Azuma. The objectives of this chapter is number one, to know the different solar cooling paths, the possibilities, and number two, to understand the working principle of solar cooling technologies. And then the outline of the chapter will be, number one, a few reminder on refrigeration cycles. Number two, we'll talk about solar cooling, but solar cooling using solar PV. Okay. And number three, we'll talk about solar cooling using exclusively thermal energy, heat. And within that, you have the thermomechanical processes and then the purely heat-driven processes. Good. As a reminder, remember that during your first degree, likely for those who have taken thermodynamics, it was said that to produce work from heat, you need a device called heat engine. And heat engine, an example is like your car, okay? So heat from the combustion of petrol, okay, will give mechanical work, okay? And that mechanical work will allow your car to move. Likewise, in steam power plants producing electricity, you have heat being converted to work. And that work comes out from the plant in the form of a mechanical work, in the form of a shaft rotating. And then with an alternator coupled to the shaft, you get electricity. So these are heat engines. So heat engines receive heat from high temperature source, convert parts of that heat into work, and then reject the other parts. Remember a little bit the laws of thermodynamics, the second law that tells you that you cannot get a heat engine that produces entirely work from heat without rejecting part of the heat. That's why you have a radiator in your car. That's why the exhaust is coming out very warm. So these are the rejected heat. When you suppress the rejected heat, so the down part from the heat engine will disappear, and you have a system that will not work. Okay, converting entirely heat into work is not possible. Part of the heat has to be rejected. That's nature. Okay, nature is made that way. And if you want heat to flow from low temperature source to higher temperature source, naturally it does not happen. Naturally, heat flows from high temperature to low temperature, much like water flows from high pressure to low pressure, okay, or high altitude to low altitude. Okay, so if you want the reverse to happen for the case of water, you need a device, because naturally it will not happen. And the device for water, okay, is a pump. The same manner, if you want heat to flow from low temperature to high temperature, you need a device, and that device is called a refrigerator. Okay. All systems that are used in order for heat to flow from low temperature to high temperature are called refrigeration systems. And on your screen, on the right hand side, you have a system, okay, a refrigeration system. And a refrigeration system, you look at it and compare it to the left hand side, the heat engine. All the arrows have been reversed, okay. So instead of producing work while receiving heat, a refrigerator will receive work and be able to pick up some heat from a low temperature and throw it away in a high temperature reservoir. So that's how it works. Good. This is an animated image to show you a little bit how vapor compression and refrigeration systems work. The vapor compression and refrigeration systems are like the conventional air conditioning system that you have in your office, or the air conditioning system that you have in your car. So far, widely, they are vapor compression systems. And how does it work? And how does it relate to the refrigeration diagram that we just saw? Here, you have a fluid circulating. But the fluid will not circulate without this device here called a compressor. The compressor is kind of sucking the fluid, okay, and then sending it. And because it sucks and compresses, it raises the pressure of the fluid, okay, and the pressure goes here, the fluid goes here, releases the heat, and then it comes back in its initial form or initial state. But because the pressure was raised up, so you need a device to lower the pressure for the fluid to come back to its initial state to form a complete cycle. Remember, a cycle is a process in which a system goes from point 1 and comes back to the same point 1, having the same properties at point 1. So if it has left this point where my cursor is with some properties, pressure and temperature, naturally when it goes through the cycle, the pressure is raised, you need to lower back the pressure for the fluid to come back to its initial state. So this device here does the contrary job of this very one. So it's an expansion device, while this one is a compressive device. Okay, so the fluid comes to the evaporator in a form of liquid. It picks up the heat, vaporizes, is being sucked by the compressor, okay, sent to the condenser. So the vapor condenses and then goes to the throttle valve or the expansion device for the pressure to be lowered and then is sent back to the evaporator, and the cycle continues. So heat is being taken from the evaporator and sent to the condenser. And the evaporator is having lower temperature than that of the condenser. The condenser could be the ambient outside your office room, okay, where it rejects the heat taken in your office room, okay, acting as the evaporator. In the case of a fridge, the kitchen fridge, so the evaporator is simply the food compartment, all right, and then the condenser is simply the coiling that you could see at the back of the fridge. Very hot, it can burn your finger if you touch it. So that's the condenser. In new fridges, you may not see barely the condenser, but nevertheless, it is there. Okay. For aesthetics reasons, they tend to hide them now, but they are there. So this is a vapor compression refrigeration cycle. The solar system will try to imitate actually the vapor compression cycles closely. So, and we'll see how. What are the options? For solar cooling processes, you have mainly two options, two big options. This diagram here shows the options. You have the thermal driven system on your right, and then the solar panel systems, electricity system on your left. And for the electricity system, you have mainly the Peltier system and then the compression system. We explain all of them, okay? If you take the thermal driven systems, within that it can be broken down to heat transformation and then thermomechanical processes. Within the thermomechanical processes, you could have the Rankine process, the Volumier process, and the steam jet cycle or steam ejector cycle. And here, for the heat transformation, you have open systems where the working fluid is open to ambient air, and then you have the closed cycles which are completely closed. The working fluid does not come into contact with ambient air. We explain almost all of them. So solar cooling follows closely the conventional vapor convection cycles that we have just explained. So much like in engines, we talk about efficiency. For you to measure the performance of a cooling system, we use the word coefficient of performance. It's a kind of efficiency. But I guess that because coefficient of performance can be more than 1, while efficiency is defined between 0 and 1, they would like to make the difference between the two. So for cooling systems, the efficiency is called simply coefficient of performance, COP. So, and how is it defined? All performances are defined as follows. You have the desired output over the required input. You have your system right, you desire a certain output, and then there is a required input for that output. So efficiency is defined as desired output over required input, COP equally. So the desired output for cooling systems is the useful cooling energy. All right? And then the required energy will be the energy supplied to the system by external sources. Okay. So for thermal-driven systems, unfortunately it doesn't show here. All right. For thermal-driven systems, the net energy supplied by external sources is mainly thermal. Okay. And then for electricity-driven system, the net energy supplied by external sources from electricity. That's the difference. Okay. Good. Vapor compression systems using solar photovoltaics. So it's no more than your office air conditioner, but instead of being powered from the mains, it's rather being powered by a photovoltaic module. So the compressor is being run using a direct current motor. Direct current because the photovoltaic module will deliver direct current. All right. So it's a simple system. It's your conventional system, but instead of being powered by electricity, okay, if it is your office or your kitchen, it's electricity from the mains, the power company. If it is your car, it's electricity generated through the alternator of the car. So here you use simply photovoltaic. So this is solar photovoltaic cooling by means of vapor compression. Good. You have the Peltier effect. The Peltier effect cooling system is named after its inventor. Peltier has noticed that if you join two dissimilar materials, say metals, okay, and then you pass current through them, you notice that one end of their junctions is getting heated up while the other end is getting hot, cooler. I will explain how it works, the physics behind it. And then people thought that, oh, but this can be used in cooling systems. This is a typical Peltier cooler. How does it work? You have the power source. You can use a photovoltaic panel. That's why we call the system a solar cooling system. But it could use other source of power. Okay? But when it uses solar photovoltaic, it's called a solar cooling system. So you have the electrons from the negative, okay, running to going to the positive. If you have two semiconductors, one doped N and the other doped P, remember again, these semiconductors are normal elements, chemical elements. You just either add some electrons in them, free electrons in them, In that case, they are doped negatively. They have excess electrons. And then the other metals you could, or other substances, you could remove some electrons out. So when you take some few electrons out, so you get a positive or p-type semiconductor. So you have created a n-type and a p-type. One you added some electrons, the other one you have taken some electrons out. Okay, where you have taken some electrons out, you have created some holes. Okay, and now if you take these two and you join them, how did you join them? You see the top is joined together, okay, and then the down is more or less joined through the circuit, okay, and then you power it. So you have the electrons. For them to overcome the gap, okay, in between two semiconductors, there is a gap, some energy gap, okay. That's if you have a carrier like an electron, it has to overcome the gap, okay, either by absorbing some energy somewhere and get the force to overcome the gap, or either to lose some energy, okay, in order to pass the gap. So here in this figure, the electrons are being circulated by the solar panel, okay, and they go through the n-type and the p-type semiconductors, okay. But in their way through, because of the gaps between the two semiconductors, the junctions, so the electrons will absorb some heat from the surrounding in order to overcome the gap and go through the semiconductor. Likewise, you see the electrons goes from the negative pole all the way to the positive pole, while the holes that were created go on the other direction. So likewise, for the holes to travel and overcome the gap, they need some energy, and they will take the energy from the surroundings. They will absorb the heat. The electrons will absorb the heat to travel from left to right. The holes will also absorb the heat to travel from right to left. And then when the electrons wants to go back, okay, to their initial state, they have to lose some energy before they go back. And how do they do that? They release the energy, okay, and they travel and they continue their way. And the cycle continues. Likewise for the holes, they will absorb the energy and then they will go, okay, through the gap, and then they have to release the energy to continue their way back to their initial state. So consequence, you have one end of the junction being cooled and the other end being heated up. So you have created a refrigeration system, okay, where it's like you have your evaporator here, the food compartment here, and then you have the condenser here. So what carries the heat is not a refrigerant, it's not a fluid circulating, but rather the electrons circulating and the holes that are circulating that picks up the heat and releasing them. Okay. So if you want to create a cooling system like an air conditioner or a fridge, this picture here shows how you can use the principle described before to create your fridge. So the food compartment is just the cold side of the Peltier system, okay? And then the hot side, if it is an air conditioner, you put it outside, okay? The hot unit. If it is a fridge, the cool side is the food compartment, and then the other side is the condenser side, okay? That's how it works. Now, you have still in the photovoltaic systems, you have a Sterling solar cooling system. How does it work? Before we look at the solar cooling system, let's look at the Sterling engine. And this animated image shows you how a typical Sterling engine works. It requires some heat source. The heat could be coming from anything, from burning gas to the sun energy, etc. In giving the heat to the gas, you have the gas, you see the small circles, okay? That's the gas. And the gas throughout the cycle does not change its phase. It remains gas. So the gas, the most usually gas are hydrogen, helium, or air, natural air, okay? So it's being heated up, and because the gas is heated up, the gas will tend to expand in volume, and in doing so, it will pushing this piston, okay, inward, okay, and then you have a crankshaft, okay, linked to a flying wheel, okay, and while this compresses, okay, so the flying wheel will return the crankshaft, okay, because of some free momentum that it gained, and push the gas back, okay. The gas will go up here hot, and then being cooled down through the fence, okay. And if it cools down, it then contracts, okay. So this type of engine, as I said, the source of heat could be solar, and the image on the right hand side shows a solar dish, okay, reflecting the sun energy to a Sterling system, okay. And once you have this system, running, you have mechanical power. Why not? You have a shaft, you have a crankshaft, okay, something rotating. You can add up an alternator and get electricity generated. We are not going to generate electricity when we are talking about Sterling solar system, using solar photovoltaics. Remember that the title is solar photovoltaic cooling. We are going simply to reverse this trend. We are going to more or less, instead of giving out the heat, we suppress the heat, and then we create the movement of the shaft by using the motor, and the motor is being powered by a solar PV. And then the reverse will be observed, okay? The reverse will simply be observed. So heat will be taken from here, okay, and then sent here. This will act like the condenser, and this will act like the evaporator, okay. So remember that the heat engines that we showed can be reversed, and when it is reversed, it is a refrigerator. So the Sterling engine is a heat engine. It takes heat and provides some mechanical work while rejecting the rest of the heat. So when you reverse it, by rather providing the mechanical work through a solar PV, you get the reverse. Heat is being taken from the cold side and sent to the hot side. And you've created a solar PV Stirling system. Good. You have, aside the solar PV cooling systems, we mentioned the Peltier cooling, and then we mentioned the Stirling cooling. One important thing that I forgot to mention, the Peltier cooling, because there is no moving parts, okay, it is a very silent machine. So unlike the vapor compression system that you have in your office, that makes some noise, the Peltier, there is no moving parts, only the electrons going around, picking up the heat and going around. It doesn't make noise. So because of that, is mostly used in military equipments. And another advantage is that it can be powered, as we spoke about, can be powered by solar PV. So it's being used in space equipments where the equipment, satellites, etc., can be there for years without human intervention. So the Peltier cooler is used to cool electronic equipment in space, for instance. Good. So aside the solar PV cooling systems, which use electricity coming from solar PV, we have the thermomechanical process. Thermomechanical means you use heat to create mechanical power. That's all. So here you have two loops. You have the sun loop, okay? The cursor is showing the sun loop. And then you have your refrigeration loop. A conventional normal vapor compression refrigeration loop, where you have the compressor, the expansion device, the evaporator, and then the condenser. So how do you turn the compressor? You use the heat from the sun through a normal steam cycle. Okay, you got to get familiar with the steam cycles, okay, to generate some mechanical work. And that mechanical work could be used to power the compressor. And if you still have some work in excess, you can generate electricity. But here, we are not generating the electricity for powering the cooling system. We have mechanical shafts, and then we power directly the refrigeration system. In you and I, in our offices, it is convenient to use the electricity to power the compressors, air conditionings, and to power the fridges in our homes. Simply because we cannot extend the shaft from the power plant of your area to your office to power the compressor. So it's not convenient. Everyone taking mechanical power from the power plant to his home to power the compressors, etc. So electricity is the most convenient form. So the mechanical power from the power plants will be converted into electricity, easy to transport, and then when it is transported back to your home or to your office, you use a motor to convert the electricity back into mechanical power. So here we skip that step. So we have directly mechanical power, and then we power our compressor. And the source of energy could be the sun. In that case, this is a solar cooling system. Good. The same way as we explained in the previous slide, you have a system, a steam system creating mechanical power, and that mechanical power powers a vapor compression system. The same way, if you have a Stirling engine producing mechanical power, this mechanical power could be used in a reverse other Stirling engine to create cooling, and that machine is called a Villemnier machine. Okay, exactly like this one, creating mechanical power and use it to power a vapor compression machine. Remember that the left hand side is just like the right hand side is just like the left hand side, okay, except that the turbine plays the role of the compressor. The expansion device will play the role of the pump. Here it is adding pressure, here it is expanding, etc., etc. So here the same way, instead of you suppress the heat here, and then you use the mechanical power that you produce here to then turn this one, of course you get some cooling, and that is called the Villemnier machine. Now the steam ejector cooler, how does it work? You know, when you are working in the speed range, the fluids are in the speed range lower than that of sound. Okay, so you are working in a subsonic flow regime, but once the flow of this the fluid, the speed goes beyond that of sound. So you are working in a supersonic flow regime. So you have in the subsonic flow devices called nozzle and devices called diffusers. The same way in the supersonic flow, you have devices called nozzle and devices called diffusers. A nozzle is a device that is used to accelerate a fluid. You know, speed and pressure are linked together. When one goes up, the other goes down. So while you are accelerating the fluid in the nozzle, at the same time you are reducing the pressure. The diffuser does the contrary. You are rather increasing the pressure, thus reducing the velocity. So, for instance, if you are using a water hose and you want to accelerate the flow of the water, just put your finger at the end of the hose. Thus you are reducing the surface area. You are creating a nozzle. So the jet will come out with much higher speed. So this can be explained by the following equations. You see, the mass flow rate of the fluid coming in is assumed to be the same as that going out in certain conditions, and mass flow rate is density times volume flow rate. So if it is the same fluid, the densities can be cancelled out. So volume flow rates are equal. But volume flow rates are simply the cross-sectional area times the velocity. So A1C1 will be equal to A2C2 from this very equation. And then if you maintain AC constant, the left hand side you maintain it constant, and then the right hand side, if you look at this figure here, A1C1 could be the entrance where the arrow is entering, and then A2C2 will be the exit. So in this case, if, for instance, you are reducing A2, for the constant here to still be constant, what happened to C2? C2 will simply go up. Okay? So the consequence is that in the nozzle, as the fluid is moving and you are reducing the surface area, you are increasing the velocity. And that's what you experience in the water hose. It's a nozzle. If you don't have a nozzle, just put your finger at the exit of the water and you'll be reducing A2. That's increasing the water flow, the velocity, C2. So, this well understood, you know that when you are increasing the speed of a fluid or the speed of anything, okay, you can increase it and go to the speed of sound, the sonic level, and go beyond that, the supersonic flow. So if in subsonic flow, nozzle have this shape, when you are beyond the sound, the speed of sound, nozzle will have a different shape, which is contrary to in the subsonic flow. It's nature, once again. That's how nature is made. So if you are using a nozzle in the subsonic flow and you keep on reducing the surface, the cross-section area, meaning that you keep on increasing the velocity, you come to a point where you get to the speed of sound, the sonic level. Okay? And if you keep on reducing again the cross-section area, of course you will not go beyond the speed of sound because you are changing to another regime, because you want to go beyond the speed of sound and go to supersonic, and you are using the device in the subsonic flow. So for you to cross, okay, the barrier, so you just have to get another nozzle in the supersonic flow regime and add to the nozzle in the subsonic flow, and you get something like this. So the fluid comes in, okay, and as the cross-section area reduces, the speed will be reducing, and up you get to the speed of sound. And then if you still want to go beyond the speed of sound, you need to still use a nozzle. That's its role, to accelerate the fluid. But because you are getting into another regime, that's the supersonic flow, the shape changes. So you have a kind of converging, diverging nozzle. And this is the main device in steam ejector cooling system. That's the main device. We explain. Because this device is able to accelerate fluids beyond the speed of sound, okay? So in doing that, remember again that when the speed is being increased, the pressure of the fluid also reduces. So when you go to supersonic flow, beyond that of sound, you are almost nearing vacuum. The pressure is so low that you're nearing vacuum. And we use that here. You know that any fluid, any liquid has on top of it some vapor. It's being illustrated in this picture. So you have a fluid, okay, in the form of liquid. On top of it, you have some vapor. It applies to any fluid in any recipient. And that vapor is in equilibrium with the liquid itself. And then if you take some vapor away, the liquid will tend to vaporize again, evaporate, and replace what you've taken away, because it has to be in equilibrium. When you disturb the equilibrium, it will tend to replace it and go back to its equilibrium. So take some vapor away, on top of it, any liquid is going to be replaced. So it's being used here. And how is it replaced? More liquid will evaporate. In doing so, it takes some heat from the surrounding. So consequently, the surrounding is getting cooler. Okay? Keep on taking the vapor away, the liquid will be evaporating, and in doing so, well, the surrounding is getting cooler. And that is used in the evaporator side of any air conditioning system or any refrigeration system. You have the compressor sucking the vapor from the evaporator, and more liquid is coming to evaporate, and in doing so, is picking up the heat from the evaporator, and that's creating cooling. And this is the same way here. Okay? So the compressor will be replaced by our ejector. Okay? Or converging diverging nozzle. So any fluid that comes through the converging diverging nozzle comes out with high speed beyond that of sound, supersonic. Thus the pressure will be almost zero, like vacuum. And that stream of fluid will then entrain some of the vapors on top of the fluid here. Take them away. And in doing that, some more liquid will evaporate, and then you create some cooling. That's the principle behind the solar ejector cooling. This illustration here is to tell you that the fluid that you pass through the ejector could be steam. Okay? And how do you get your steam? You can use the solar system to generate your steam. So you have the solar collector, you have the generator generating the steam, and then you pass the steam through a convergent divergent nozzle, and while it is going in high speed, it will entrain some of the vapor from the evaporator. So more vapor taken away, more liquid evaporating, and then in doing so, it's taking the heat from the surroundings. So we are creating some cooling. That's how ejector cycle works. It's not more than that. If you like, you have in your conventional vapor compression system, you have the throttling device, you have the condenser, you have the evaporator, and then you have the compressor. So this section here more or less replaces the compressor. It's the ejector. Okay? This is being used for cooling, but in industry, ejector is also used for drying products, soap, and other products. The food industry. Okay? So imagine you have your food and you want to take some vapor away from your food, some moisture away. You want to dry it. Just have an ejector, okay? Have some steam to go through it. It will entrain the vapor away, and then you get your whatever gotten dried. Okay. Now you have the heat-driven systems. Okay. And the heat-driven systems, you have open systems and then closed system. This is an example of an open system. The open system, the working fluid is open to ambient. Okay. Imagine if this is the house to be cooled. Okay. Here the working fluid is air. Okay. You take air and you pass it through a material that absorbs moisture. Okay. You have some materials on the market that people use in their wardrobes in order to prevent humidity going into their clothes. So these materials are not different from our desiccant wheel here. They are desiccant materials, meaning that they absorb moisture. Okay? If instead of having them in your wardrobe, you have them in the form of a wheel that rotates, and then you let some stream of air pass through the wheel, so the moisture from the air will be absorbed. So the air will come out a little bit dry, less moisture in it. Okay, and the absorption through the desiccant wheel is it releases some heat. The reaction is kind of exothermic. So consequence, the air will come out dry, but it's going to be hotter than it came in. And then you don't want hot air to be sent to the room. What do? Use a heat exchanger to take up that heat. So consequence, you have a very dry air, but relatively cool. Okay? And for you to enhance again, to reduce further the temperature of that dry air, is dry air. So there is the ability to absorb moisture. Okay? And any dry air absorbing moisture, okay, we kind of cool down. Okay? It's evaporative cooling. Okay? In very dry climates, Saudi Arabia, Burkina and Co., they use a lot of evaporative coolings because the air is dry, the air can absorb moisture, and doing so, the air cools down. So just put some water somewhere, and a fan blows through that water, okay, and then puts kind of be putting some water into the air, okay, and in doing so, it's like the water evaporates and it takes the heat from the surroundings, so cools down. So the air is kind of cool. So when you do that, you have a cold air, okay, relatively cold air, but with some moisture in it. It doesn't matter. You send it to the room, okay. People use it, and then you return it, you reject it, okay. You can add more water in it, and then for it to be able to pick up some of the heat here, okay, through the heat exchanger. The heat is very important because at the beginning your desiccant will absorb moisture, and you need to recover that moisture for the wheel to still work, okay, because the seal is there turning, okay, and working. So you have absorbed moisture through the wheel, so you want to regenerate the wheel, okay, so you need to take some of the moisture away. So and you do that through heat, okay, and the heat can be provided by the sun, okay, solar heat. It could be provided by any other source of heat, okay, but we are talking about solar cooling, so we don't go beyond that. So the solar collector will provide the heat, but because this is coming out warm And this wheel here has taken some heat away. This is going to preheat the air, the returning air. And then the air is now completely heated up by the sun and then being sent through the wheel again. Okay, the wheel picking up and the air picking up the moisture back from the wheel and going to the atmosphere. So this is called a desiccant evaporative cooling, DEC, desiccant evaporative cooling system. Okay, a deck system, and it works fine, especially in climates where you have a little bit of relative humidity in the air. Okay, it will not work in dry climates because the air is already dry. You want to play around. You don't need this wheel here. If the air is already dry, from here you just add some water to the air. It will cool down. You send it to the room. Okay, but for climates where relative humidity is relatively high, you could use a desiccant wheel to absorb the moisture, okay, and do the process. Okay, this figure here explains how it works. So process air coming in, desiccant dehumidifier, it takes up the heat, okay? So you get some dry air, and then you spray some water in the dry air, the air gets cooled, and you use it. And then you need to regenerate your wheel. You can use any other source of heat to do that, but because your air is already warm from the room, you can use that with a solar collector to regenerate your wheel, and that's all. That's how desiccant evaporative cooling works. It's a heat-driven, solar heat-driven, open system. Open in the sense that the working fluid is being thrown to the environment. This is a closed process, heat-driven but closed process. In the previous process, you didn't see any mechanical kind of device. Okay, here it works more or less the same way. For instance, if you take this part is like the compressor. So it looks bulky, but that is how it is. It's like the compressor, and then you have the condenser, expansion valve, evaporator. So all these systems, solar system here, replaces the compressor in the conventional vapor compression system. And I explain how it works. So you have the vapor from the evaporator that has to be sucked away, kind of sucked, okay? And there is a substance here called the absorber that does the job. So it's kind of sucking the working fluid, the vapor, and in doing that, more vapor, more liquid will evaporate, and then it will create cooling. Now, if you want the cycle to complete, you need to go through the normal, cycle. Okay? So you have kind of absorbed the vapor by a certain substance that has some compatibility with your working fluid, ability to be absorbed. So when it is absorbed, okay, so the mixture here has to go through some system so that they can be separated, and then the cycle will start again. And how do you do the separation? So you then need to pump the mixture. You pump it to a kind of boiler. We call it generator. okay? And the generator here, you need to provide some heat. It's a mixture of two liquids, okay? Or a liquid and a gas, okay? So you need to provide some heat in order to separate the two. So you make sure they have different, boiling points or different, so you provide the heat and then you separate the absorber fluid, and then that will come back to its initial point, okay? And then the working fluid that was absorbed, then we go the way back and the cycle starts again, okay? As I told you, all this system replaces the compressor. And these type of systems, okay, instead of being powered by solar energy, can be powered by any other source of heat. In my village, since I was kid till now, there is no electricity anyway. They use a refrigeration that use this type of system, absorption systems. And the heat is being provided by either kerosene, mostly kerosene, okay? The missionary, the white fathers, came into my village with this type of fridges, and my family also used some of them. They are just powered by something burning, providing the heat, and they work very fine, okay? I wish to have some pictures to show to you, but I'm sure many of you have already seen fridges working with heat, not solar heat, kerosene, or any other form of, thing that you can burn, okay? They are absorption systems, okay? Absorption, AB, absorption systems. Good. You have the closed systems. Basically the absorption system, not to be confused with absorption. AB, absorption, and AD, absorption. Okay? The difference between the two, at times people tend to explain it in a manner that the absorption, AD, is a substance that can absorb either liquid or gas. AD is absorption, is a solid that can absorb either a liquid or a gas. So the absorber here, that is a substance, we tend to absorb vapor from the evaporator. The same principle applies here. Vapor taken, more vapor more liquid we tend to evaporate for the equilibrium. And in doing that, okay, it's going to be taking the heat from the surrounding, so the surrounding will be getting cooler. Okay, so the sorbent or the absorption substance at a point we get saturated because it's going to be doing that, and at the point it will absorb almost all the fluids. Okay, and at least you will get some cooling by the time it does that. Okay, and then you need to regenerate back the working fluid so that the cycle will continue. So you can do the regeneration on the right hand picture with solar energy. Okay, you have the solar collector, the sun coming in, okay, and then it regenerates the working we built one of these solar cooling system here as a fridge. I mean here at KNUST as like a fridge, whereby during the day the sun appears and does the regeneration. Okay, it does the regeneration, and during the night the cooling process starts. Okay, so you can create enough ice to cater for the needs of the day. Okay, the cooling needs of the day. Okay, I'll show you a picture that is in Ouagadougou at Touaï, where my colleague Yawazuma is, where the adsorption, AD absorption system is being used to cool a building. This is the building. You have the solar collectors on top of the building, okay, providing the heat, okay, and then it's being used inside, okay. This is like a cooling tower sort of, acting like the condenser, okay. And then you have inside the room all these equipments, okay. Unfortunately, they are bulky compared to the conventional electrical, vapor compression air conditioners. They are very bulky, yeah. But it doesn't matter. The sun is there and it is free, okay. If you can compromise on space, you can use these equipments. Good.